Now we will discuss about joint probability distribution where more than two random variables may exist. Take an example. If car is not being started, there may be two possibilities. One, fuel tank is empty or battery is off, down. So both events can be considered as two different events. When such kind of conditions happen, we take the help of joint probability distribution. And in joint probability distributions, both the events, both the random variables may be discrete in nature, may be continuous in nature. Both the random variables may be independent or dependent. That we can later find out how we can understand whether both are dependent events or independent events. If they have any conditional probability existing, definitely they will be dependent event. But if there is no zero conditional probability, then there is no possibility of dependency. So they may be considered as independent event. Let's have an example. It will be more clear to us. We will solve the problem and we will understand what the joint probability. See the basic definition of joint probability distribution. A function having two random variable x and random variable y. One may be whether fuel tank is empty or not. The other may be the battery is down or not. We can have many other examples, whether machine is working or the operator is available. So availability of the operator, working of the machine, both may be two different random variables. This was the principle for discrete joint probability distribution, where events x and y both are discrete in nature. They are not continuous random variable. So if they are not continuous random variable, we will apply the formula of summing all the probabilities over the sample space must give you the value 1. And this f x comma y is nothing but the probability of having x equal to x and probability of having y equal to y. So there is an and relationship between these two, which are represented by this probability of x comma y over the sample space A for x and y. So there may be many possibilities for x and y. Take this example here. Let x denote the number of times a certain numerical controlled machine will malfunction, either once or twice or 3 times on a given day. Let's y denote the another random variable that defines the number of times a technician is called on emergency and the machine is not working. Their joint probability distribution is given here. The values of f, x, y are given over here. These values are given over here in the table. But how do we obtain these values? Let's take an example over here. Suppose 1000 times you take an observation. For x, number of time machine malfunction once, twice, thrice. Operator is called on emergency 1, 2, 3. If you count 1000 occasions, such occasions, and out of those, if 50 occasions had one emergency call and once machine was not working. The other, suppose 50 times again, twice machine was not working and once operator was called on emergency. Thrice machine was not working, suppose 100 times. Then 50 times for this combination 2 and 1. For this combination, suppose 100 times. For this combination, suppose 350 times. For this combination, suppose none of the situation occurs when 3 times operator was called on emergency and once the machine was not working on the given day. Same thing here. It's suppose 200 times, suppose 100 times. The sum of all these will be 1000. Let's have over here 200, here 500, 300. Count over here 100, 2, 3, 350, then 550. 550. Sum of these. When you divide this 50 by 1000, you get the probability of f x equal to 1 and y equal to 1 as 50 by 1000 gives you 0.05. Now suppose I want to know the probability of getting machine malfunction 3 times, x equal to 3, and operator is called on emergency twice. We can see that this combination is this one. Machine malfunction 3 times, let's have a different color. 3 times is this. Operator is called on emergency twice is this. In this case, we have this 350. It will be 3. Change the color again. 350 divided by 1000 gives you the probability of occurrence as 35. But here, if you remember our previous lecture about conditional probability, then suppose I give you a case, probability that machine will malfunction twice if it was already known that operator will be called or was called on emergency once. So this is what we call conditional probability. Based on the formula, this probability is nothing but related as P of A and B is equal to probability of A and conditional B multiplied by probability of B. So in such conditions, this will be nothing but probability of x equal to 2 and y equal to 1 divided by probability of getting y equal to 1. So what is probability of getting y equal to 1? Probability of getting y equal to 1 will be the condition when you have once operator is called an emergency irrespective of the machine's malfunction. So that is the total sum 200, which will be divided by 1000. So the probability is nothing but 0.20. So this will be, so this term will be probability of 2 and 1 is 0.05 and probability of getting y is 1 is 0.2. So this probability will be 1 by 4. Now see what is asked in the problem. In the problem, they are looking for evaluate the marginal distribution of x. Now, before describing the marginal distribution, you should know that it is the probability of getting x over the domain of x, which is nothing but 1, 2, and 3, is the probability of x. Now, what is marginal probability? Let's go back to that first. Now, before moving to the marginal probability, I want to explain you what will be the conditions for continuous joint probability distribution. Let's see here. In this case, x and y are same, two random variables, but both are continuous random variable. When they are continuous random variables, we cannot deal with the sigma sign. We have to integrate over the ranges, and the range may be the domain of x, the sample space of x and y. So if this comes 1, it will be the probability distribution. And when x and y are continuous, it is called as continuous joint probability distribution. In both, either discrete or continuous, in both cases, we should know what is marginal distribution. Marginal distribution is nothing but the distribution of either x or y irrespective of the other random variable. So if you have to calculate the marginal distribution of x, you have to sum up all the possibilities for the y domain for that particular value of x. In case of continuous, you have to integrate for all the possibility over the range of y for that particular value of x. Now see this. Now come back into the example. What is marginal distribution? As we see this probability, what is the probability of getting x as 1? So getting x as 1 is nothing but all three conditions which may occur. X is 1 when y is 1, or x is 1 when y is 2, or x is 1 when y is 3. So what is the probability that x is 1? Has the probability of getting x1 and y1, or probability of x1, y2, or probability of x1, y3. So now in this case, or is replaced by plus. So this is nothing but the probability of 0.05 plus 0.05 plus 0.000. So it is nothing but 0.16. That will come over here 0.10. Here it will be 0.35. Here it is 0.55. So these will be your marginal probability distribution for x. So this is gx. Same here for marginal distribution of y, it is 0.2. That we refer as hy. 0.2, 0.50, 0.30. For the values of y equal to 1, y equal to 2, and y equal to 3. So these will be marginal distribution. I can write it very clearly here. So marginal distributions for x, gx, for y, hy. 1, 2, 3, 1, 2, 3. For this, it is for x 0.1, 0.35, and 0.55. 0.10, 0.35, 0.55. And there it is 0.20, 0.50, 0.33, 30, which we see over here. Now. So now these are marginal distributions. So this sum of all these probabilities will also be 1.0, 1.0. That is why they are called probability distributions. This is what I have already explained to you, that in case of conditional probability, this is what I have already explained to you, that in case of conditional probability, we have to follow the basic formula of probability A when given B is nothing but equal to probability of A and B divided by probability of B. The same we are implementing for discrete random variables as well as for continuous random variables. Now take another example before ending for continuous joint probability distribution over here. Take this example for continuous joint probability distribution where X and Y are continuous random variables. What they ask for? Marginal distributions and a probability for a specific condition. First see Gx will be nothing but integration minus infinity to infinity fxy dy. But in your condition is that y vary from 0 to x and x vary from y to 1. So now in this case y vary from 0 to x. So 0 to x 8xy dy. That will give us a value now here see this will be 8x y square by 2. That will give us a value here from 0 to x. So 2, 1, this will be 4. So this is 4. X is a constant. Y will be x square minus 0 square. That will be 4x cubed. Now, if we have to find out the marginal distribution for y, so hy will be integration minus infinity to infinity fx comma y dx. But for the x, the range is y to 1. So this will be y to 1, 8xy dx. Now see what will happen in the next line. 8y x square by 2. Range is from y to 1. So 1, 4. So 4y is a constant here. But in the bracket it will be 1 square minus y square. That will be 4y 1 minus y square. Now these are two marginal distributions, but when we have to find out the value of p, just change the color. We have to find out the value of probability x more than 0.6 when y is given as 0.5. So for this we have to see the function fx comma y upon hy, that we have to integrate for the range of dx from 0.6 to 1.0 for the specific value of y 0.5. So what are the functions here? Functions here are 8xy divided by 4y 1 minus y square. So y will be cancelled out, 4 will give you 2, integration 0.6 to 1.0 dx. That will give us a value 0.6 to 1.0 2x upon 1 minus y square. Dx. The given value of y is 0.5 because this is what we want, x more than 0.6 when given y equal to 0.5. So that is integration 0.6 to 1.0 2x upon 1 minus 0.25. That gives dx. This will be 2 upon 0.75 constant, x square by 2, 2 is cancelled out, and that will be limit from 0.6 to 1. So that will come out as 1 minus 0.36 divided by 0.75 gives us 64 by 75 as the answer to this probability condition for joint probability distribution. So this was all about joint probability distribution. I hope this will be very useful for further understanding, further calculating certain conditions. For example, number of traffic light encountered on the way to the office and number of traffic light encounters on the way back to home. So these may be considered as two different variables, two different random variables. Based on that, we can understand the probability of occurrence. So we can find out the expected number of traffic lights. We can find out the probability of occurrence of the certain number of traffic lights encountered. So these are certain conditions where joint probability distribution is a very useful tool to understand the probabilistic situations. Okay, see you next. Okay, see you again in the next lecture. We will understand how to find out the expected value, how to find out the mean and variance of a particular distribution. So until now we understand what is random variable, how we can generate the marginal distributions from the joint distributions, or how we can find out the probabilities from different probability distributions. Thank you very much.